This laboratory will focus on the RF mixer. The RF mixer has two inputs, an RF signal and a local oscillator signal. Those two signals enter the mixer, and the output is the sum and difference of the two frequencies that were input. In order to use the signal for demodulation, we must pick one of those two signals, the sum or difference. In general, we always pick the difference frequency and filter out the sum frequency. And that is the job of IF filter or intermediate frequency filter. The end result being an IF signal, which is based upon the RF signal. The modulation, however, or information is unchanged. We will now look at this in the frequency domain. In the frequency domain, the AM signal is represented as the RF signal. This is our radio station channel frequency. The LO signal is simply an oscillator, sinusoidal oscillator at a given frequency. After the mixer, we have the sum and difference products. The difference will be equal to the LO minus RF, and the sum will be equal to the LO plus the RF. That is assuming that the LO is greater than the RF signal, so-called high side injection, the LO being greater or higher than the RF. That is not required, but that is typical. When the RF signal is modulated, we of course create a lower and upper sideband. In this case, we're assuming sinusoidal modulation of the carrier. The LO is simply still an oscillator at a given frequency. But now the two mixed signals are different. They both contain the sum and difference of the USB and LSB signals along with the RF signal shifted by the sum and difference frequencies. The end result after the filter, of course, is then just the repeat of the RF signal, but shifted to a new frequency. This frequency will be fixed by the IF filter, and the local oscillator will be changed. So we will look at that situation with specific frequencies. Now let's assume our desired radio station is 1070 AM or 1070 kilohertz. It is modulated sinusoidally. The local oscillator will now be set to 1070 plus 455, which is 1525 kilohertz. Now why 455? Because that is the IF filter frequency. So in the mixing process, we create a 455 kilohertz, which is the difference between the local at 1525 and the RF at 1070. Of course, we also produce a sum frequency, which is 1070 plus 1525 or 1595 kilohertz. After the filter, we are only left with 455. This is the superheterodyne process with the IF filter. Now we'll look at a change in frequency for the desired AM signal. Now we have changed our AM signal to 690 kilohertz, the desired AM radio station. The local oscillator will now change to 690 plus 455, 1145 kilohertz. Again, the 455 is fixed by the IF filter. When we look at the mixing products, the difference will be unchanged at 455. However, the sum will now change to 690 plus 1145 or 1835 kilohertz. Again, after the filtering of the IF, we end up with 455, which is unchanged from previously. So the AM signal at 690 got changed to 455 kilohertz. This is an update to the mixer laboratory for ETE 335 in spring 2016. You have the handout and the explanation about the basic mixer operation, the actual mixer picture, the device itself, and the circuitry involved. If we look at the circuitry, you will notice it is simply a combination of RF transformers and diodes. These are special diodes for mixers. Now, some of the critical information is actually on the mixer itself. The mixer is limited to 40 milliamp of an input signal. In a 50 ohm system, that is 2 volts peak in 50 ohms. So you must keep your voltages below 2 volts. Now you will also see, if you check the data sheet, and I've excerpted part of it in the back of the report or in the handout, and you will see that we need 5 milliwatts on the input signal of the mixer, which is the L input. So we need to calculate how many dBm 5 milliwatt is. So 5 milliwatts is voltage RMS over 50 ohms. If we do the calculation, that means that 250 milliwatt ohms is equal to VRMS squared. So VRMS turns out to be the square root of 0.25 from the milli factor, and that gives us a VRMS of 0.5 volts. Now for sine waves, we know the relationship between RMS and peak is 0.707, or the inverse 1.414. So for a sine wave, that is a 0.707 volt peak sine wave, or a 1.414 volt peak to peak sine wave. But that's only for sine waves. Other waveforms, you need to calculate the actual voltage for those waves. So we are looking for an RMS voltage of 0.5 volts, or a peak voltage of 0.707, or a peak to peak of 1.414 volts. Now on a spectrum analyzer, of course, we always read in dBm. So we need to convert 5 milliwatts into dBm. That is easily done. 10 log 5 milliwatts over 1 milliwatt. Remember, the M in dBm comes from the milliwatt reference, 1 milliwatt reference. So that is 10 log of 5. That turns out to be plus 7 dBm. It says the calculation is 6.97 dBm. But plus 7 is the typical value associated with 5 milliwatts on a mixer. So now we need to set up the mixer for plus 7 dBm. So I've adjusted my signal to be 10 megahertz and 6.98 dBm, which is very close. So we'll go look at the generator. So the generator, if you look closely, you will see that the amplitude is 2.95 volts. Or 3 volts peak to peak. So by calculation, we had 1.414 volts peak to peak, or double of the calculation. Why is this? Well, the generator is a 50 ohm output. The spectrum analyzer is a 50 ohm output. Also, the generator can be set up for either assuming a 50 ohm output or a high impedance output. It gets confusing, so you must trust your measurements. So we trust the spectrum analyzer to read properly at plus 7 dBm. In the generator, there is a setting you could change to a 50 ohm load, and that would adjust the value. But for now, we're going to treat this as 2.95 volts peak to peak results in a plus 7 dBm signal. Now we can look at the spectrum by looking at the frequencies between 0 and, say, 50 megahertz. That'll give us at least 5 harmonics. And there we see the signal. Our main signal at 10 megahertz, second harmonic, and a third harmonic. And pretty clean after that. If you want, you can save that value for review. Now I have turned on the ARB generator, the Agilent, and connected it to the spectrum analyzer, and I see the display. The voltage on the ARB generator starts out at 100 millivolts, which is quite low. That is safe. That's minus 16 dBm. So we need to adjust this voltage for the plus 7 dBm to compare the two. We've made the adjustment and we see we're at 10 megahertz and 6.97, very close to 7 dBm. If we look at the generator now, we see the 1.47 volts peak to peak. So this generator is set up for a 50 ohm output load with the voltage. So that you must be very careful about. So now we are set to check the spectrum, and we see this spectrum is a little bit higher second harmonic, third harmonic, and even a fourth. There might even be a fifth out there if we expand the frequency. Stop frequency of 100 megahertz, and we see, well, not too much, but a pretty good similar frequency span, slightly more harmonic content in this generator. Re-looking at the Regal generator with the setup to 100 megahertz, again we see a little bit cleaner spectrum. So we will be using the Regal generator as our LO signal and the Agilent signal generator as our RF signal. So in the first part of the laboratory, you'll connect the Regal generator plus 7 dBm and the RF generator at 0 dBm into the L and R ports of the mixer and examine the frequency spectrum output. Since we have already set up the LO generator, the Regal, we only need to reset the RF generator, which is the Agilent unit. So I've adjusted the signal. We have about 0 dBm, and that's 650 millivolts. So you should record those values so that you don't have to re-measure the signal each time. So I have connected my plus 7 dBm signal, 5 milliwatts, into the L input, the 0 dBm from the RF generator into the R signal, and the yellow signal is the X output. Now this is the spectrum we see. This is 0 to 100 megahertz. We're going to zoom in a little by defining the frequency to be 0 to 30 megahertz. The first peak we see is at 5 megahertz. This is the difference frequency between the local, which is 10 megahertz, and the RF, which is 5 megahertz. We'll confirm that later. The next peak, 15 megahertz, and we can see that come up. You'll notice that those two are very close to one another. Minus 5.6 dBm, and the next peak is at minus 6. The sum and the difference signals always track together. Now we see something else just to the right, 25 megahertz. These extra signals, some of them are connected directly to the LO and RF, some are what we call intermod products. Again, if we go back to the larger frequency span, 100 megahertz, we can see that there are many other products involved. The mixer is great at changing frequencies, but it also produces many new frequencies that we need to make sure we can filter out. For our purposes, the key frequencies will be under 30 megahertz. All right, so now we take data as the lab suggests. You will change the frequency of the RF signal. As I change that frequency to 6 megahertz, you will see a different display. But again, the peak signal is at 4 megahertz. That's the difference signal. 10 minus 6 is 4. And the next peak is the sum signal at 16 megahertz. If you change to the amplitude mode, of course, in the linear mode, you will see only two signals, the difference and the sum. But we need to work in the log mode because it shows the smaller signal. In part 2 of the lab, you will do something similar to part 1, but now you will change the local oscillator frequency, again focusing on the sum and difference components. The third part of the lab, you will change the level of the RF signal, that is the Agilent arbitrary waveform generator, and just to see the response of the system. Part 4, you will add modulation to the RF signal and then look at the product. So I will turn on the AM signal by using Shift and AM. You see an AM indicator. Under that case, the frequency of modulation is changed by shift frequency, the level by shift level. So we will change the frequency of modulation, and it is set at 100 Hertz. We'd like to use something like 10 kilohertz, so we'll enter that number, 10, and then kilohertz. So now we have 10 kilohertz modulation. If we want to check the level, it's 100%. MA is 1 or 100%, which is okay with us. So we're good to go. Now when we look at the spectrum, you don't see much happening, maybe some bouncing up and down of the markers. But the reason why is that 10 kilohertz modulation cannot be seen in a frequency spectrum of 30 megahertz. So I am going to look at my peak signal, which was our difference signal at 4 megahertz. So type frequency. I'm going to put the center frequency, which is the top button, at 4 megahertz. Now we see our 4 megahertz signal in the center. Now we need to zoom in a little bit, and we're going to use the span control. Under the span control, I can adjust this to a value to see that 10 kilohertz. Well, if the spectrum we need to see is 10 kilohertz, which is very small, I need to have about 100 kilohertz, so each square represents 10 kilohertz. So I'm going to set my span to be 100 kilohertz. Now we see a very weird looking display, and that's because we need to adjust the resolution bandwidth. The resolution bandwidth is 30 kilohertz, which is not enough to view the spectrum. Now when I push the auto, it changes to 3 kilohertz, and we see our two sideband components. If I change it to manual and go to 1 kilohertz, I can see them even easier. Again, in the linear mode, you would see them as the carrier and the two sidebands. They're very much reduced, but those are them. Now we can tell that because if we turn off the AMs, the sidebands go away. So we only have the carrier. Now to confirm that those signals are also produced at the sum frequency, we will type in the sum frequency value, which was 10 plus 6 megahertz or 16 megahertz. So we go to frequency, center frequency is 16 megahertz, and of course we see our two terms. The center frequency is 16 megahertz and the modulation. Again, if I turn the modulation off, they go away. So this is our sum signal and the difference signal. They contain the same frequency information. Now if we want to look at this on the scope, we can do that, but we will get a surprising view. When we connect the X signal out of the mixer to the scope, we get a mess. It's a very complex system. The auto trigger helps not at all. We need to use the single sweep. So when I press single sweep, you can see the signal. Now this is a very complex looking signal because it involves many frequency components, the sum, the difference, all the intermodulation products. So we must do some filtering after this, and that is the next step. But that is the sum and difference signals viewed in the time domain. This is mostly worthless for us to view, but that's what a sum and difference signal looks like in the time domain. Now the solution to the messy looking signal we saw on the scope is to use a filter. This is a little filter in here. It's a 455 kilohertz filter for AM receivers. Input, output. Now we will view the signal on the spectrum analyzer, but first we need to match the filter to our input signal. With a 455 kilohertz AM filter, we need to use a local oscillator which is 455 kilohertz above our desired frequency. In this case, we will use the desired frequency of 1070 kilohertz. So enter number 1070 kilohertz. That's our AM signal, and the local oscillator will be set at a frequency of 1525 kilohertz. So frequency 1525 kilohertz. Now when we do that, we need to go back to our frequency span. Frequency now 455 kilohertz. And we see our AM components. Now if we look at the sum frequency, which is 2595, frequency 2595 kilohertz, we don't see much there. We see less than we saw previously because the filter is reducing that signal. So let's look at that again. 2595 and frequency of 455 kilohertz. Much larger signal in the... Now we can look at this signal on our scope. Now if we look at the signal, now we start to see a classic AM signal. Again, you must adjust the triggering on this, but there is our classic AM signal. Now we can turn off the AM, shift AM, and of course all we will get is the carrier. But in this case the carrier is not our original 1070. We need to actually measure the frequency, and you will see that it is 455, 454.5. So where did that come from? Well, the filter only allowed the difference frequency of 455 through, and so that's what we see. Let's go back and review a little bit of those signals with a zoom in on the spectrum analyzer. So this is the spectrum with 1070 kilohertz RF and 1525 as the LO. If we check our peaks, the 455 is the difference signal. The next peak is at 2.6, that's 2595. The signals are -6 dBm. So we have lost signal from the mixer. We started out with 0 dBm on the generator, and now we're at -6. Now the 455 is where the modulation was. Also it was on the sum frequency, but we want to get rid of all this other frequency content with the filter. So now we'll insert the filter. So the filter has been inserted, and we see a dramatic change. We see loss from the filter. Now we're at -30 dB. The difference frequency is strong. The sum frequency is less so. Again, 455 for the difference signal, that's the peak. The next peak is at our 2.6 megahertz or 2595 kilohertz. So that's what the filter has done for us, and we saw the display. For this final section of lab, if you want to do what a radio does, you can change your RF signal, such as to 690. In that case, the local would have to be 1145 kilohertz. So with 690 kilohertz on my RF signal, my oscillator, local oscillator, is now 1145 kilohertz. And when I go back to the frequency spectrum, I see the peak signal again at 455. So although I've changed the local and the RF, the difference product stays the same. And that is the genius of the Superheterodyne receiver, is that you can change your RF input by changing your LO signal, but the same information is transferred. If I turn on the AM modulation again and type in frequency 455 kilohertz and adjust my resolution bandwidth to something less than 1 kilohertz, adjust my span to be 100 kilohertz, we will see our AM signal. So everything is converted to 455 kilohertz in the Superheterodyne system. Now FM radio uses a different IF frequency, 10.7 megahertz, but all radio systems use this technique. Very few use any other method in their receivers. So that is the end of the lab. Check the handout, and if you have questions, let me know. Please be careful about the signal levels associated with the two generators because the voltages could damage the mixers.